All right, welcome to the first lecture in Physics 3030, the universe. And today we're going to be talking a little bit about history, and of course, history really of cosmology and astronomy. And this is just a history mostly of people noticing the sky, but not just noticing the sky, but making scientific advancements and understanding about what was going on in the sky. Now, we all know that many cultures have myths about the sky or where we are, what our position in the world is. And there's a famous Native American myth about the flat Earth sitting on top of a big turtle, right? And the turtle is what carries the Earth around. So this is one that a lot of you are probably familiar with. We're going to steer away from myths, though, and we're really going to just talk about, again, what information people started to acquire back in the day. So let's first start with the Egyptians, okay? And just to have some idea of what they understood and what they knew. They knew about equinoxes, which an equinox is when the length of the night is equal to the length of the day, and the solstices, and the solstices are the longest and shortest day. And I imagine you know that the longest day is in the summer, and the shortest day is in the winter. And they also could do things like correlate the appearance of stars. So specifically, they correlated the appearance of Sirius, also known as the dog star, and they correlated this to the floods, so the spring floods on the Nile, which was really useful for them because they didn't have levees and dams to do anything with when the floods were coming. And they also knew about the fact that 1 year doesn't just equal 365 days, but it actually has a quarter thrown in there. So it's 365 and a quarter days, which is, of course, why we have the leap year, to make up for this quarter of a day that comes every year. And the Babylonians, who lived in what's present-day Iraq, were around, they overlapped a little bit with the Egyptians, and they could do things like calculate when eclipses would come, calculate the appearance of these eclipses, and predict them. And I think most important for the Babylonians, there were other advancements as well, scientific advancements, but they kept detailed records. And this is really the key here. They used something called cuneiform, which is impressing little nicks and lines into clay tablets. And because they kept these detailed records, they passed on information, not only their information, but the information of the Egyptians. And this eventually made its way to the Greeks, who we'll see were very, very important in this whole scientific process. Let's show a picture of this cuneiform. So let me close this ink layer then. So here's a picture of the cuneiform, and you can see there's little impressions here and there, and you just turn the stylus and move it around and impress. And there's a whole alphabet and a whole language here, and this information, this tablet, was known to the Greeks. So when the Greeks found them, they knew what the Babylonians and hence the Egyptians had been up to. Okay, so back to another clear slide here. Let's start with the Greeks. Come on now. Here we go. And this is the ancient Greeks, of course. And we'll start with Thales of Miletus, who is sort of credited with being the father of science. And this is about 600 BC. And we could talk a lot about ancient Greek science, but I just want to, again, highlight some of the astrophysical and cosmological information these guys had. And he was seen to be the first scientist because he used the natural world to explain things. Basically, if you couldn't see it, then it wasn't a good enough explanation, the natural world to explain things. And he also is credited with stopping a 5-year war by predicting an eclipse, which is pretty amazing. The next Greek philosopher slash scientist I want to talk about is Aristotle. He had one of the first solar system models, and his model had 55 concentric spheres, okay, with of course the Earth at the center at this time, and these huge spheres that everything moved around the Earth, and then way out on the outside something called the prime mover, which was even outside of the stars and made everything on the inside spin around. He also didn't believe the Earth was flat, couldn't prove it, but he believed it. He believed this because when you see an eclipse, okay, so this is the moon now. When you see an eclipse and you see the shadow of the Earth that comes between the sun and the moon come across it, it doesn't come across with a straight line. It comes across with a curved line, and as you go, it kind of looks like this thumbnail moving its way across the moon. And that's why he didn't believe that the Earth was flat. Now, of course, it could have been flat circle, so it was really hard to prove any of this. Okay, let's do some erasing here. And we're going to start talking about Aristarchus. Now, you've probably heard of Aristotle, probably not Thales of Miletus, but Aristarchus, he gets a bum rap, and he's a guy that you probably should have heard of before. Now, Aristarchus is famous, because he is credited with actually coming up with the first heliocentric solar system. And as we'll see, this is sort of a theme that keeps coming up over and over again. This is a very easy way to predict how things are moving around out there, how the planets move around us and how the stars move around us. And of course, heliocentric means sun is sitting in the center, the Earth moves around it, and all the other planets move around the sun as well. Now, of course, this really butted up against the beliefs at the time of what people thought. Everyone thought that the Earth was the center of all things, and that things fell back to the Earth because they wanted to be back at the center of the universe. That's why they thought everything fell back to the Earth. And in fact, this theory, this heliocentric theory, was disproved. And I'll say disproved because, of course, we all know this is to be true, by a lack of what we call parallax. Now, parallax is a very important visual effect that we'll talk about in great detail in the next couple of lectures. But basically it means if you close your eye, if you close one eye and then the other eye, it sort of looks like things move from right to left. And this is actually what we do have parallax in our eyes because they're set a little bit apart. That's actually how we can tell the depth of something. So our depth of vision has to do with this parallax. And the idea was that if the Earth was moving around the sun, the stars in the background when we're at one side of our orbit or the other side of our orbit should look like they've changed position a little bit. Now this does happen, and the problem is that at the time it was just too small to see. And we can see it nowadays, but not even with all stars, just with closer stars. And we'll talk more about parallax as it comes. But this is an interesting lesson, right? This idea that this was disproved. And science is always changing, right? What we know is only as good as the instruments that we have to measure it, right? And I'm a theoretical physicist. There are experimentalists out there, and the experimentalists are taking my theories and my predictions and trying to find them out there, or just trying to measure things and seeing if they fit in with what we know about the Earth. And you will see that this is a very important theme that we'll see over and over again. This was disproved back in ancient Greece, but it was actually the truth, or at least the truth as we know it today. And so this is the idea. Science can always change. And we'll talk more about that sort of as we go along in this class. Okay, the next Greek philosopher slash scientist slash astronomer that I want to talk about is Ptolemy. And Ptolemy is really important. He actually predicted a solar system that was Earth-centered, Terra-centric, if you want to call it that. And the thing was that it couldn't just be like Aristotle's system where everything was on a sphere, because you could see that the planets don't really move on spheres perfectly around the Earth, because you can look at the stars, you watch them over time, and it doesn't work that way. Oh, spelling things wrong here. Solar system. So instead of using just big spheres, he had a system that had something called epicycles. And epicycles are, you have the Earth, and you have the planets, and there's a center of the epicycle, and then there's some circle, right? So there's another planet here. So this is like Mars or something. And this circle goes around and around, and then that circle moves around. Now, there's nothing here at the center, right? So there isn't anything actually sitting there at the center of this epicycle. It's just that Mars moves around some center point that keeps moving around the Earth. Now, that's what it sort of looks like. Now, if I was to actually draw a picture of this, right, as this went around, it would look something like this, which is a really strange way for something to move, right? This is funny because things on Earth do not move this way. And even though that was the case, let's see. Get rid of this here. So they don't move this way. And even though we never saw anything move this way, we were so ingrained to have the Earth at the center of everything that we said, okay, this is a really complicated system. Nothing on Earth moves this way, but we're going to accept it. And until the 1600s, this was the accepted way about how everything moved. And you could predict how things move, but it made the math pretty complicated, as you can imagine. Okay, now I want to sort of recap a little bit here about the Greeks. So, Greek recap. And that's that through Thales, The Greeks introduced the principle of explaining their observations by natural causes, right? So everything had to be caused by some natural cause, and by natural means something that we could measure, something that we can see. And they still believed that everything was Earth-centered, and as I alluded to before, this is why objects fell back to Earth. Because they wanted to be back at the center of the universe. Everybody wants to be at the center of the universe. Okay, so that's where we're at right now. Now let's move on to European astronomy and cosmology. Okay, this is really the Renaissance era. I throw in astronomy and cosmology there. People were thinking about cosmology at this time, but so much of it was steeped in mythology and religion and different views that it was really the astronomical advances that we're thinking about here. Now, these are names that hopefully ring a bell a little bit to you as we go through the list of European astronomers. Copernicus, who is a Polish priest, and just to give you some ideas here, I'll throw some years up just so you know what kind of years we're talking about. He was a Polish priest, and he came up with a heliocentric model, again sun-centered, of the solar system, and he started using this, and he was really careful to say it's a good mathematical tool, right? It's not that that stuff isn't going around the Earth. It's just that if we just imagine that everything was moving around the Earth, then the math is just way easier. So let's just do it this way. Let's just do the math this way, okay? But we don't really have to say that the Earth's not at the center of everything. It's just if it wasn't at the center of everything, the math would be way easier. Now we're sort of leaning towards something a lot of you may have heard of, that a lot of us refer to as Occam's razor. And this is an idea in science and in life in general that the simplest idea, well, not idea, but the simplest explanation is often true, is often the explanation. Okay. And in the case of Copernicus, he really didn't want to tell people that he thought the Earth was not at the center of things, but it turned out to be the simplest explanation. And we'll come back to this over and over again. We'll see that Occam's razor often comes back to be the best way to decide what the answer is. Okay. Copernicus was so careful because the church was really angry about folks who said that, no, the Earth isn't true. And a guy named Giordano Bruno, who was an Italian cosmologist and priest, was actually burned at the stake in 1601 for saying that he believed in the Copernican idea. Okay, so it meant a lot to actually try and change these ideas of what was going on. So let's talk about a Dutch nobleman named Tycho Brahe. I really like his name, Tycho Brahe. And he was a nobleman, lived from 1546 to 1601. And he also came up with a geocentric model where basically what happened was, well, so he came up with a geocentric model which is Earth-centered, right? So you got the Earth here. But he was so in tune that he had all of this data. So he collected a lot of data. A lot of data. And he had this way of taking data and measuring it really accurately. And he had a lot of data to work with, and the data just made it seem like everything was orbiting the sun, right? So you got, let's say, Mars here or something. Everything is orbiting the sun, except that he could not let go. So he said, okay, what's happening is everything is orbiting the sun except the Earth. The sun is still orbiting the Earth. So basically you've got this big clump of stuff over here, that is orbiting the Earth. But everything else is orbiting the sun. And of course this is moving on some little epicycle, or else this wouldn't all work out the way it was supposed to. Which, again, seems overly complicated, and we know it to sort of not be the case, right? Okay, so let's clear this and move on. So Tycho Brahe's assistant in the Netherlands there was a man named Johannes Kepler, and he was famous for his laws. So laws of planetary motion. And he sort of inherited Tycho Brahe's data set, which was this huge data set, biggest data set of anyone at the time in one place. And there are many of these laws. One of the neater ones is that all orbits are elliptical. So all the orbits of the planets are elliptical. So now we're sort of getting away from the circle idea. So now you have the sun over here, the sun, and instead of it being a circle, you have an ellipse. So this is just the Earth's orbit. It's not a perfect circle, some elliptical thing. And there's two focal points in the middle of the ellipse, and one of them is at the sun. And this opened it up again. Calculations to predict where things were going to be are greatly simplified. And he was, again, also careful not to really talk about what was at the center and what was moving around. He also said, well, this is just really good math. And around the same time, is a very famous guy named Galileo Galilei. And Galileo used a new tool of the time called the telescope, which all of you probably have looked at or used. And he used a telescope to look up at the sky, which it was hard to see things far away. And one of the most important observations he made was the 4 moons of Jupiter. And when you look at the 4 moons of Jupiter, you see these big things. They're about the size of the Earth. They're at least as big as our moon. And because these things were moving around Jupiter, right, it implied that Earth was not the center of everything, right? If Earth was the center of the universe, then the moons should be orbiting the center of the universe, which is the Earth. And so this was a huge earth-shattering idea, that there's moons around Jupiter, they're going around Jupiter, and they're not going around the Earth. And so this started to put some cracks in the walls of what was held dogmatically at the time to be the belief, which was that the Earth was at the center of everything. And then he had another observation, which were the phases, let's go back to black here, of Venus. So if you look at the planet Venus, right, that's inside of us. It's a planet closer to the sun. And if you look at it through a telescope, you see that it has phases just like phases of the moon, right? There's shadows on one side of it, and because of what side the Earth is on the sides of Venus. And these phases could only be explained by the Copernican / Keplerian model. And this was it. This was the beginning of the end of the geocentric model of solar systems. And of course, Galileo was greatly appreciated by everyone at the time, and of course he was put under house arrest for the rest of his life by the Catholic Church for such crazy ideas. And of course, he did publish some papers and snuck out some papers out of his home to thankfully pass on this information that, of course, we know to be the truth nowadays. So, one last guy I want to talk about, and that is one of the most famous physicists. One of the most famous physicists, and that is Newton, Sir Isaac Newton. And I want to talk about Newtonian gravitation, but so Newton was around from, 1642 to 1727, something like this. And so besides his 3 laws of motion, which describes how everything we see around us moves, and of course, besides inventing calculus, he came up with a breakthrough idea. Okay, and this idea was that the same force that makes objects move, or that makes objects fall, objects fall on Earth, keeps the Earth moving around the stars, keeps the Earth around the stars. Okay, so the idea here is let's just play a little game, right? We're sitting here on the Earth, and we throw something in the air, and of course it falls back to the Earth, right? Whatever goes up must come down. This is what we see. Now you're on a flat Earth, and at the time now they know the Earth is round, but okay. Throw this straight up, comes back down. And he says, well, I could also shoot something like in a cannon. So this is me maybe throwing a ball. This is just some little ball, right? But I could also shoot something out of a cannon, okay? And I can shoot it really far, right? So shoot it out of the cannon. Here it goes. Falls to the ground over here. But then he said, well, the same thing, right? If I just shot it far enough, so instead of shooting it out of there, maybe I could shoot it far enough that it would start going around the Earth. But what if it just kept going? What if it's this some perfect amount of speed that it just kept going in a circle around the Earth? Now, there has to be something pulling it in this direction, right, to make it keep curving around the Earth. Because that's what's happening here, right? This thing is going down. Here it is. This thing is going down, but it gets pulled back to the Earth, back towards the center of the Earth, just like a ball does, right? And so this thing on the outside, even though it's going in a circle around the Earth, is getting pulled back towards the center. He said, well, that's exactly what the moon does, right? The moon moves around us in a big circle. And why does it keep moving around us in a circle? Because the force of gravity is keeping it there. And this may seem like a really simple idea right now, but at the time this was amazing, an amazing breakthrough, and he got this idea, and then he used it to describe everything that was going on around in the closer solar system. So this is the amazing thing, is that gravity actually explains Kepler's laws. One simple equation actually explains Kepler's laws. And so they can be derived from, they're derived from gravity. And this is what we mean by great physics laws, right? You have the law of gravity, and then all of these laws, these three laws that Kepler comes up with, are, though they're all separate laws, they can all come from the law of gravity. And I'm going to just write this equation down for you guys. The law of gravity looks like, there's a minus sign in there, big G, which is some constant, right? Just some constant, times the two masses, how big the two things are, over the distance squared between them. Okay, and we'll come back to this a little bit. We're going to use this equation a little bit later on, and we'll talk more about it. We're going to really be more concerned about just how big the force is anyways, not what direction it is. So we can, let's just forget about that. Let's see if I can just erase that. There, okay. We're going to forget about that. Minus sign for now. Okay, so we'll come back to that in a little while. I want to talk about one more thing before I let you guys go from this first lecture here. Let's talk about one last thing, and that's something called Olber's paradox. Now, Olber was alive around the same time as some of these guys, and that paradox is concerned with one of the simplest observations we can see, and that is that the sky, the night sky, is mostly dark, right? You look out there when there's no moon, when it's not the nighttime, or it's not the daytime, and it's mostly dark. And there's a little bit of talk about this in your book. I would like you guys to read a little bit about Olber's paradox, and we're going to talk a little bit about it. But the idea is that because because the sky is dark, mostly dark, this implies that the universe is of finite age, is a finite age. In other words, it hasn't been around forever. And this has to do with the fact that if stars are around forever, and there are an infinite number of stars in infinitely every direction, then there would be starlight in every direction, coming from every direction, from an infinite amount of time ago, and it would be lit up. So the night sky would be lit up. So, night sky would be lit up. Because it's not lit up, the stars must not have been around for all this time. Now, today we know stars die and are formed on the order of 6 or 7 billion years. 6 to 7 billion years, right? Which is about how old our star is. And so there's a little crack in this idea, but this is the type of logic that we're going to start looking at more and more, and trying to figure out if we can understand more about the universe. Now, I hope this lecture hasn't been just a list of things that you already knew. Some of you may have known this, some of you may not have, but this is the interesting sort of evolution of our understanding of what is going on in the sky and how we came to start to put together the model. This has really been a history more of anything about the heliocentric model of the universe. And we're going to show how this got proved more and how we can use the same sorts of logic that started in ancient Greece to come up with new and exciting things about our understanding of the universe. So, until next time, thanks.